Hi, good morning, everyone. This is Spiros Athanasiadis from ICCS. I would like to present you Ingenious project and the next generation integrated toolkit that we're developing for collaborative response, increasing protection and augmenting cooperation capacity. ICCS is the coordinator for this project. ICCS stands for the Institute of Communication Computer Systems and is located in Athens. It is a public scientific and technological institute which undertakes advanced research in the field of electrical and electric and computer engineering and technologies. It has 12 research units, 24 research labs, more than 800 researchers, and mainly contracts with European Commission, national authorities, agencies, and industry. In our project, we have 6 end users, we mean first responders, 6 SMEs and industries, 1 partner which is expert in legal, privacy, ethical, and social and human security factors, and finally 10 research teams and universities. In total, we have 23 partners from 13 countries. Ingenious developing, integrating, testing, deploying, and demonstrate the next generation integrated toolkit for collaborative response, which ensures high level of protection and augmented operational capacity to respond to the disaster scheme. We're developing a lot of components, and we're dividing our solutions in 3 main categories. The first is the smart devices that are attached or mainly are for the first responders. The second category is the smart devices in the air and on the ground with mainly different type of drones. And finally, we have the platforms and backend solutions that help us to multi-fuse data, have expert reasoning in your data, and create one common platform for the command center with a central view of all the tools. Also in this category, we have augmented reality solutions and mobile applications. In the first category of smart first responders, we have mainly a smart helmet, which is equipped with 2 cameras, 1 regular camera and 1 infrared camera, which help us to recognize videos live stream from situation as smoke, fire, with a low light, and provide live feedback from the field to the command center. Also, this tool equips with a voice communication module, which is provided by directional communication between the first responder and the command center. We have a uniform and some wearables attached in the uniform. The main parts of the smart uniform are the battery management system, the central process unit, and the communication module, which supports a communication channel for the rest wearables to interconnect with the overall platform solution. We have also the boots that are acquiring data from different type of sensors and integrated them into a 3D printed insoles. And we have sensors such as pressure, force, accelerometer, gyroscope, and magnetometer. The recorded raw data are transmitted in real time to the main processing unit of the uniform, and through the communication channel that use low energy protocols, we send this real-time raw data to the central application. We have also a K9 vest, which is provide awareness from the canine location. Also, it has two video streams, high definition and a thermal camera, and also provides a bidirectional audio between the K9 units and the operator of the K9 unit. Finally, in this category, we have a gas sensor that is aimed to measure carbon monoxide and ammonia in there, regarding the concentration level, using mid-IR laser technology. And the main novelty of the ingenious laser-based mid-IR gas sensor is that it uses indirect detection. In the second category of the smart devices in there and on the ground, we have a set of different types of drones. We have the MINS, the micro indoor drones that are intended as small and disposable devices to provide indoor organization of the first responders. A group of drones enter the building, scatter the land on the floor and other surface, and with ultra wideband beacon can create a mesh network and provide an indoor map for the first responders. We have the MAX, multi-purpose autonomous exploring drone, which is providing a map for outdoor and indoor of the location is deployed. We have indoor position system, IPS, which is a system that attaches in the helmet and can provide, in combination with the rest of the drones, a map of the places that the first responders are navigated in the incident scheme. And we have the MAC, which is a very large drone which can vertical take off and land. It is deployed when the first responders are in the incident, and provides an overall map of the searched area. Finally, we have for the communications. The communications are deployed in the field. The equipment has been selected to provide proprietary communication infrastructure and access to a resilient network that will support all the needs of our toolkit in the field. And currently, we are providing a personal area network, PAN, a LAN, a local area network, and a wide area network. Now, in the last category of our solution, the commanding and common operational picture, it is a set of software solutions, so platforms, applications that collects the data from all the sensors in the field and provide all the data in the COP, in the Common Operation Picture, which is the main platform. We have a Fusion Engine, which is able to integrate multiple source through its infrastructures and utilize the data gathered for the extraction of conclusions, providing real-time situation awareness and decision support functionalities to crisis operators. We have expert reasoning, which is a module aims to support the decision-making processes of the first responders that are involved in a disaster. In particular, use the available data from sensors and from other analysis components in order to provide useful insights that enhance the management of first responders and their resources. In this group of solutions, we have also an augmented reality response platform, which is provide seamlessly delivered notification alerts and visualizations as an augmented reality services to the first responders while conducting their operations. This platform relies on information coming from other ingenious components to display relevant information to the user wearing the glasses. We have also in this set a worksite application, which is a mobile version of the overall platform, aiming to have in any handheld device the main status of all the components in the current situation, and have, let's say, a cloud online light version of the COP. We have also social media application, which is aims to provide to the ingenious system with crowdsourced information by collecting real-time manner social media data, mainly from Twitter, analyzing the architectural and visual content to enrich with additional information and allowing the end users to view the collected and analyzed tweets in a friendly user interface. We have also a face recognition application, which is receives pictures from other components in the field and running algorithms were trying to provide data regarding the information received. Mainly, we're focusing to receive data and try to identify victims and analyze pictures with low lighting or dust. We have also a multilingual operation application, which is a service that provides speech-to-speech translation to support multilingual communication between first responder groups and the command center. And the main functionalities and let's say the main modules of this application is the automatic speech recognition, which is responsible of transcribing the input source audio into text, a machine translation module that is in charge of translating the source language text into target language text, and then text-to-speech module, which is in charge of converting the large language text into output audio. And the main reason that we have this application is to provide cross-border missions with different teams from different countries. And finally, we have the COP, the Common Operational Picture, which is the main cloud application aiming to have it in the command center, which is collects all the information from the field and allows to the operators in the command center to have an overview of the incident and the current status of the rescue mission. So in this slide, we can see an overall solution of Ingenious toolkit with, let's say, the whole ecosystem having in the center of the command center the main cloud application platform, which is collects all the data from the field, from the different type of rescue teams. And we have some main key points for each tool and the benefits that we have. Within Ingenious, we have a very rich validation program to test and provide our solution to the first responders and receive feedback and evaluation to continue our developments. In total, we have 27 laboratory integration and testing sessions, 18 small-scale field tests, and 2 full-scale field validation exercises. Currently, we have already conducted 2 rounds of leads and 1 round of SSTs. And almost all the tools have been tested in the lab and also in the field in real conditions, and mainly used by the first responders that are in our consortium. For this year, in the upcoming period, we have 1 last round of leads that will be conducting the upcoming month. And we're going to have a full-scale exercise hosted by SAMU in France, May 2022. We're going to test in the same field test the whole toolkit. We're going to have actors from different type of first responders. And receiving the feedback that we're going to have, we're aiming to have the last round of SSTs and the second full-scale exercise, aiming to finalize the developments, provide the third prototypes of each device, and be ready to have the whole toolkit ready for our last full-scale exercise. Currently, in all these lab tests, SSTs, and the full-scale exercise that are conducted or planned for the upcoming period, we're trying to have a realistic situation and scenarios. So we have also here some indicative solution scenarios that we'll have to validate our toolkit. We have man-made and natural-made scenarios, aiming to have real conditions for testing our components and, of course, the whole toolkit. So I would like to invite you to join us in our social media, in the Twitter, in the LinkedIn, in our YouTube channel, and of course in our website. In our YouTube site, we have videos from the demonstrations that have been conducted from most of our tools of the toolkit. And also in the website, you can find newsletter and the current status and the upcoming events if you would like to join us. For any details, you can contact us at the email info@geniusfirstresponders.edu or directly the coordinator of the project and of course of my team, Angelos Amditis, at his personal email. So I would like to thank you again for viewing this presentation for Ingenious project. And I would like to share with you one video that we have prepared for demonstration in the upcoming events where we highlight our tools and what we're doing in this project. So thank you again. I will stop the camera and please continue with this video.
seamless communication between multilingual services. All the operational information and subsystems on the map environment will be displayed at the control coordination system. This will act as a central visual interface of the ingenious toolkit. Control support also as a simulation environment for different scenarios in crisis management. 23 partners, researchers, and professionals of the scientific and business world, as well as civil protection organizations all over Europe and valuable expertise in achieving the ingenious objectives. Next generation integrated toolkit is provided to the first responders for testing and validation as part of the rich training, testing, and validation.
Hello everybody, thank you very much for the opportunity to talk about Cursor project today in the FAST European Union and Japan Symposium. Before I start talking about Cursor project, shortly about me. My name is Tiina Ristmäe. I am the coordinator of Cursor project. I am working for DHW. This is the German government agency for technical relief. I'm also the vice chair of IFEFRI network. This is the global network to advance the first responder innovations. And also I am leading DHW EU research proposals team. So now to Cursor project. In Cursor we have two main aims. Firstly, we are aiming to reduce the time to locate and detect victims trapped under the collapsed buildings or debris, and at the same time we are also aiming to increase the personal safety of search and rescue teams. And for these two aims, we are developing soft miniaturized underground robotics, different sensors, which help first responders to accelerate the search and rescue process and increase their personal safety. So the first responder involvement is very strong in Cursor. We have altogether 5 practitioner organizations involved. And also we have 10 technical and research partners. We have collaboration with Japan, with Tohoku University, and the project duration is 3.5 years. So about the same time next year we have our main results and outputs achieved in Cursor project. So to talk about the structure in Cursor, then we have these pillars or bases based on what every activity in Cursor is taking place. So we have a scenario. We have chosen earthquake scenario to be the basis of all the development work. We have also defined the use cases based on the scenario. In Cursor, we have chosen the INSARAG assessment, search and rescue levels, and we are concentrating on ASR 2, 3 and 4. These are our use cases. Also, it's important to see what kind of gaps first responders having at the moment, what is missing, where they need advancements, where they need new technologies, and this is also done in the Cursor project. Then we move to the second pillar or fundamental basis of the Cursor project. This is the first responder requirements. So we knew what are the gaps, what we are missing. We knew what is the scenario we are moving in or acting in. So we started to look into the functionalities, into the requirements, what we are looking for in the new technologies, how the technology should work, what kind of tasks it has to fulfill, and so on. So after this job, the technical partners took these requirements and built up the Cursor system architecture. So the architecture is defining how different components are communicating with each other, what is the logic between different components, and also they define the technical specification for all Cursor circuit components. So also important is to mention that that training and knowledge transfer have a very important role in Cursor. In order to understand the technologies, to test them, to use them, the first responders need to be trained. And we are talking about new technologies, innovative technologies. This is not their technology which is familiar for them in most of the cases. Also, we have gathered a lot of knowledge, know-how, new information, which we are collecting and providing also to project stakeholders. These fundamental activities are basis to develop the technologies. Without these, we cannot really be successful. So then when the technology development has started, we move into the phase of technology testing. And in Cursor, as you can see also in the coming slides, the testing has very important role, and it's something that it takes place throughout the project, not only at the end. Here, very important is the strong involvement of first responders in every phase of the testing. So here, just to conclude what we have in Cursor, the circuit components are the Smurfs, soft miniaturized underground robotic finders. We have drones, we have geophones, communication and localization system, and decision support system. All of these solutions or components, of course, have subcomponents, but this is the main structure of Cursor circuit. And now we are looking into the components in more detail, starting with Cursor in the air. So we have altogether 4 different drone types. So I would start with a mothership drone. This is cabled drone providing first responders 24/7 situational awareness. This drone has a very powerful camera, megaphone, Wi-Fi opportunity, but the main benefit is that through the cable the activity is continuous. The drone doesn't have to land, and it provides additional feature during the search and rescue mission. Then here on the right hand you can see the 3D picture from one rubble pile or debris. This is done with Cursor 3D modeling drones. We use DJI Mavic Pro drones, and to accelerate the process, we can use 5 drones simultaneously to do the pictures. Also, a little bit quicker process is to get an orthophoto of the area, also possible with the same drones. Then we have transport drones. As you can see here on the picture, these can be are used for transporting the Smurfs on the rubble pile, and similar model is used in Cursor project to get the situational awareness. So the aim is that the drones can be used simultaneously either in one work site or in different work sites, so to accelerate the process of locating and detecting disaster victims. And now we move on the ground. Cursor on the ground is including Smurfs. So here you can see the Smurf has different sensors. In the middle, between the wheels, there is Sniffer. This is the artificial dog nose. Sniffer is sniffing different gases. It is detecting CO2 level in the air, which is one indication of human presence, possible indication. Also, Sniffer has sensors to measure different proteins in the air, which indicate human presence. Also, the Sniffer can differentiate between deceased and alive human being. Additionally, we have different cameras on the Smurf, speaker, microphone, LED lights. So all these sensors are supporting each other. If I cannot use Sniffer, I can use the camera or infrared camera, or if I cannot use the cameras, I have the Sniffer, or I can use them all simultaneously based on the situation. On the right hand geophones demonstrated. Geophones are not a new technology for first responders. They are broadly used already now. In Cursor we are advancing the system. The sensors first responders don't need to climb on the rubble pile to mount the sensors. It can be done in front of the rubble pile, away from the risk to get injured. This is a major advantage compared to the existing system. Also, the filtering system is improved. So here you can see on the top picture there is one sensor, but the geophone kit itself includes 3 sensors, so you can do the triangular measurements. Then to support all the communications, we have in Cursor communication and localization system. Here on the left hand you can see the picture of localization system, which help us to localize Smurfs, which in turn help us to localize the victims. On the right hand you can see the central emergency gateway, which provides us the communication between different tools and provides the intelligence to first responders to make decisions. Then very important is to provide this information to first responders so that they can make decisions. For that we have common operational picture. This is a software which is used in the user coordination cell to get an overall information about the deployment, about the resources. And then on the field we have COP terminal, which is used by team leaders also to collect information, to share it with COP, and also to make decisions in the field. And here in this picture you can see all the components in action. And here I would like to say that that it is possible to use all the components together simultaneously, either in one work site or in different work sites. But it's also possible to use single components of Cursor Circuit. For example, only mothership drone or only Smurf. It is based on the decision of first responders. So now to testing, which is a very important part in Cursor, but in my opinion it should be very important part in all the research projects. In the tests we can see the needs for improvements, to confirm that the development is going on the right direction. So in Cursor we have iterative testing methodology. We started with lab tests, then we moved to small-scale field tests. These are mostly component-based tests. So it means we are testing one component here, for example, only drones or only Smurf, with some exceptions, which I explain a little bit later. Then we move to the use case tests, where the first field integration takes place. And finally, the large-scale field trial, where all the Cursor components are integrated and tested in the field. So let's start with lab tests. Yes, they obviously take place in lab conditions, and it can be an indoor room, or it can be conditions where we only test different or specific materials to understand how the technology is working in single materials. Due to COVID, unfortunately, all the lab tests were conducted remotely, or the first responders involved were only from this country where the test physically took place. The challenges here are that the technology has very low maturity, and it is for first responders quite difficult to see the potential, see or imagine the functionalities which will be developed in the next phases. And on the other hand, for technical partners, it's also difficult to show all the potentiality of the technology. And here, of course, exchange communication is helping to mitigate this challenge. Then after lab tests, we are moving into small-scale field tests. As I mentioned, these are component-based testing, but not always. In Cursor, we also started already in the small-scale field test with some integration. For example, information communication tools already had the initial integration in the first tests. Very important here is that we provide a realistic scenario as much as the maturity of the prototype allows us to provide it. Even more important is that in this test, first responders have to have hands-on testing. It's not observing, it's not demonstrating, it's hands-on testing. It means that first responders are flying the drones, navigating the Smurf, putting together the communication systems, so that they are really able to evaluate the technology, give suggestions for further improvements. Very important here is the training component. So in order to use the technology, they have to be trained. Here, of course, we cannot train them to be a professional user of this certain component. Firstly, we are looking into certain profile. For drone testing, we are inviting the pilots to test the drones. We are not training the pilots from the scratch. So there should be a specific profile already, or expertise already available before the tests. Challenges here, obviously the pandemic created a lot of challenges. Since it is hands-on testing, it cannot be done remotely. So we had here some postponements with the tests. Also here the low maturity might cause some problems. All the functionalities are not there, or first time testing in the field, some improvements have to be done. Again, important is it's testing and not demonstrating. This requires previous communication with technical partners. And the training is also somewhat challenging because we have time constraints to do the training, and also since it's a new technology, we need to have the necessary time so that first responders are familiar with the solution. Use case tests, this is the next phase after we are finalized with field tests. So at the moment we just finalized with small scale field test. Our last Smurf test took place a few weeks ago. So now, next week, we are having our first use case test. It takes place in Germany, and this is the first field integration for cursor in the air and communication systems. So we have the drones, we have communication system, we have also the COP and COP terminal. So actually we can play through the whole deployment process using these technologies, and this is something that we are going to do next week in Germany. Also important is to continue with training and to decide or discuss about the tactic, when to use what component, what makes sense. This is also part from this test. And then the second use case test, this is the use case test 3. It means assessment search and rescue level 4, where the thorough search and rescue is done. And here we are involving additionally to drones and communication systems, also the Smurfs. So it can be called like a rehearsal for the large scale test. And here we are integrating actually all the cursor components in the field first time. Here again, training is crucial and tactic decisions also very important. And of course, these both tests are very much hands-on. Even we desire that that technical partners are not using the technology. They are of course supporting technical first responders, but mainly first responders are using the technologies. And then the final test, large-scale field test, we are planning it to have in November in Athens, Greece. So this is the integration of all the cursor circuit components. Training, very important here again. And the final output should be validating the cursor technology in a realistic scenario. In order to start with exploitation plan. So here again, explanation is important, communication is important, and in cursor, since we already did it during the testing phase, we know what certain number in cursor case is meaning. And field testing. So we have in the project a schedule for testing, and in the moment we started with testing, we saw that the schedule is very tight. We need much more testing as we have in the project planned, resources planned. So we have to somehow manage with existing situation. So the schedule is very tight. And also what we've noticed is that there is different understanding among project partners. And here I will come back to the testing, demonstrating, observing expressions. First responder understanding from field testing is hands-on testing in a realistic environment. That's why we are in the project. That's why first responders are included or are participating from the lab tests. So this is something that we had to clarify in Cursor project, how we understand the testing. So this discussion brought a lot of clarity, and also we changed some plans, but it was really important to do in order to have the common understanding and common expectations to the tests. So to conclude, what are the major outputs so far in Cursor? We are very proud that we have first responders involved in all the steps. It's not easy. It's for first responders also challenging to understand all the research and development process details, and vice versa. Also for technical partners, it's not easy to understand the everyday life of first responders. but it's possible. Then we have defined our scenarios, use cases, key performance indicators, which help us to have the iterative testing and technology development. At the moment, we have the second prototypes available for all the Cursor SARKit components. They have been tested in field conditions. We are very proud of the collaboration with other similar projects like FASTER or Ingenious Assistance Respondron you have already heard of probably. Very important is the early start of exploitation strategy. I talked about the challenges in the previous slides, so that's why it's important to understand the exploitation aims together in the consortium, involve the stakeholders in the early stages. So that's what we have done in Cursor. And very important is to consider the first responder needs when developing the new solutions. It's not a secret that many research projects will not be developed further after the project end. And here one condition to be developed further or to get the needed support resources to continue the development is that the technology is validated by first responders and they declare their willingness to use this technology. So with this message, I would like to conclude my presentation. Thank you very much for the invitation. I wish you interesting sessions, interesting symposium. Here on the Cursor webpage, you will get more information about the project. There are several videos and all the contact details. So if you have questions to me or our technical coordinator, Dimitra, we would be very happy to help you further. Thank you and enjoy the next sessions.
Morning, everyone. My name is Deborah Robles. I am a PhD student at the Communication Department at the Polytechnic University of Valencia, Spain. And today we are going to share the first pilot demonstration that we held on the Assistance Project. Assistance Project is an European project, ongoing project that stands for Adapted Situation Awareness Tools and Tailored Training Scenarios for Increasing Capabilities, Enhancing the Protection of Fire Responders. So, as a matter of introduction, while war first responders are currently facing large natural and man-made disasters that put their own lives and those of thousands of others at risk, on disasters like wildfires, terrorist attacks, industrial incidents, big floods. Assistance system and architecture has been designed on the outcomes of several questionnaires fielded during the preparation phase by 18 first responders European organizations. And from the beginning, the main goal was to develop a project extremely focused and tangible solutions. In order to accomplish that, assistance will enhance the system awareness of the first responders organizations during the mitigation activities through the integration of new paradigms, tools, and technologies. For example, drones, robots, first responders are equipped with a lot of wearable sensors, and the main objective is to increase both their protection and their efficiency. The robots and drones, swarms, all those smart wearable sensors are equipped with specific sensors for covering the first responder specific data that will be needed. As will be seen on the image, the architecture schema, it's integrating a complete situation awareness platform that all the first responders can see on their tablets. And the assistance platform, it's also capable to offer different configurations modes for providing the tailored information need for each first responder organizations while they are working together to mitigate the disaster. For example, they can see a real-time video and resources location for the firefighters, but the emergency health services are more interested on see the evacuation route status, so they can switch their configuration of the HMI. Going on with the presentation, among the increasing natural or man-made disasters, first responders from assistance project are going to test some different use cases. Those are an earthquake on Turkey, an industrial plant on the Netherlands, and a terrorist attack on a bull ring on Spain. Although in each pilot, we will be focusing on different innovative modules. Now we are going to see how the system will be tested was tested on the first pilot. It was an earthquake on Turkey. And that's the aim of today's presentation. As I mentioned before, we are going to describe the first pilot. But before of that, I'm going to talk a bit about the image. The overall assistant architecture, its components, interactions, and information flows are described in the figure. Summing up a little bit, the SAP receives all the information from the different sensors deployed on the field. That can be also robots, drones, and wearables, as we said, that are attached to firemen and other first responders. And the information exchange paradigm has been selected for this. It's a published subscription approach. Now, for the earthquake scenario, it took place in Izmir last January, and the incident description was that it was really a big earthquake that had magnitude of 6.2 on the Richter scale with a duration of 45 seconds. Sorry, that's a misspell. And the emergency call center received information that fire broke out in a warehouse and the harbor at some buildings near the port, and they collapsed completely, as you can see in the image. That's the incident. All the red points were the victims that were located on the all over the place, and we had some areas. The incident one, it was the red one. We had the triage area meant to evacuate the victims and made a triage of to see how several it was the injuries. Drone area to land and deploy the drones, and we were all on the command central room on the blue spot. The capabilities tested on the pilot were messaging. The first responders and the command post sent and received different messages to the final exercise. All the messages arrived perfectly. The drone integration. The drone video flows were visualized from the command post and on the tablets of that the first responders were wearing, and new victims were detected or using that resource, and also the building stability was checked with the drone. The first GPS location, all the first responders installed the tracker client app, and all of them were registered in the SAS. Therefore, all the integrations, all the first responders were deployed on the map, and we could see where each of them were at all time. About the wearable sensors, different wearable sensors were carried out by the first responders during the exercise. Vital signs were used with a air plug, and the wearable cameras were attached to some first responders in order to also have a view of what was happening on the field. Regarding geographic information system, several GIS capabilities were tested during the exercise. For example, distance measurements, 3D terrain view, and so on. Also, the visualization of the taxi plumes were simulated and displayed on the map. Once the plumes were received, a message that was sent to each first responder team. They could visualize the plume and check whether its teams could continue working without danger or not. Another capability tested was the secure evacuation route. First responders test the secure route generation capability, asking for a secure route for evacuation in ambulance with the victims from the pilot site to a hospital in the city. And the system calculated the route and showed it on the platform and in the tablets. As the least capability, the ad hoc communication network, since the incidents scenario had that collapse all the network systems, our partner BSET, responsible of the communications, agreed with us for giving network coverage to the whole exercise area with enough bandwidth for the foreseen data and video flow exchange. The solution was composed by different Wi-Fi access points, completely wired and distributed strategically through the coverage of the whole exercise area. And to conclude and see all the capabilities and the description that we have mentioned today, I would like to share with you a video that summarizes the demonstration.
we have successfully tested all the capabilities that we will provide to the first responders in order to increase their safety during the rescue operations and also their efficiency in order to rescue the victims of whatever kind of disaster. We have tested here the integration of drones, the integration of real-time video from wearable cameras, the integration of wearable sensors in order to take
Assistance projesi bu first responder dediğimiz polis, itfaiye, ambulans ekiplerinin olay yerinde hastalara daha güvenli bir ortamda müdahale etmeleri, onların yerlerinin tespitinde yeni teknolojilerin kullanılması, bunların durumsal farkındalıkların artırılması için yapılmış bir proje. 7 ülkeden 18 partnerle çalışıyoruz. Ülkemizi Acil Ambulans Hekimleri Derneği olarak biz temsil ediyoruz.
Responders is not going to do all the things because the machines, tools, robots will do afterwards. It's only a question of the decades coming.
Dronlarla olay yerini gözlemleyerek, güvenliğimizi kontrol ederek ve komuta merkeziyle yine aynı şekilde teknolojik ortamlarda iletişim kurarak hastalarımızı tahliye ettik. En hızlı ve en güvenilir yolla müdahalelerimizi gerçekleştirdik. Umarım gelecekteki eğitimlere yön verecektir bu projeler. Harika bir deneyim oldu. Çok teşekkür ediyorum.
Burada önemli olan daha hızlı sürede müdahale edebilmek, aynı zamanda daha güvenli ortamda bulunabilmek. Çünkü örneğin bir gaz varsa bunun anlaşılması sağlanmakta.
That will be all for today. I hope you have enjoyed the presentation as well as the video. And thank you so much for your attention.
Okay, shall we stop?
Yep. That's all the presentation.
Good morning or good afternoon or good evening, depending on what time zone you are in. I would like to thank you very much for this kind invitation to take part in this very important symposium. And I look very much forward to taking part also in the live sessions. And hopefully in the future also to have the opportunity to meet like we used to in the old traditional ways of having symposia and conferences in the past. I know it sounds very much like centuries have passed since the beginning of the global pandemic, but I'm old enough to remember the old good old days of attending conferences. I'm here on behalf of my colleagues at the Consortium of Respond Day, which is the next generation equipment, tools, and mission critical strategies for first responders, and also from all the 32 partners of the project. And I'm presenting here on behalf of my colleagues in the European University Cyprus Center for Risk and Decision Sciences team, myself, Dr. Cleo Varianou Michelidou, and Iason Asenekis, who are very, I wanted to mention their names, not only for any other reason, but to acknowledge their enormous help they provide to the project and myself. The project is funded by Horizon 2020. It started in actually in 2020, so it is a 2020 project. under the call for technologies for first responders. It is a 36-month project, so a 3-year project. We are now halfway. So what I'm gonna give you the presentation, plus I'm gonna give you an update of what is happening at the moment. And unfortunately, I would like to start by the fact that last summer, 2021, was a dramatic summer for us here in Southern Europe, especially in the eastern part of Southern Europe. It was a very dramatic year, which was documented internationally for many reasons. And I believe I mentioned this because I believe that our project has relevance to that. And I believe that you are going to uncover this as the time goes. Let me just acknowledge my partners in the project from various places around Europe, around the European Union. And we are very thankful to Horizon 2020 for funding this project. What are the aims and the objectives of this project? The aims of the objectives and the objectives of this project are very straightforward, and I dare say that they're very traditional, they're very down to earth, they're very everyday type of aims. First of all, we look forward to developing technologies and utilizing existing technologies, because this is a major part as well, not only for us, but for the Horizon 2020 calls, to provide early assessment of possible catastrophe. Secondly, especially for us that we come from a traditional safety environment, research environment, we would like to provide safety assessment to the actual first responder, because the aim of the call is on technologies for first responders and providing a healthy and safe work environment for the first responder is of paramount importance for the project and the call. And also based on the 2 points above, so on the early assessment and the safety assessment, to provide risk mitigation capability. So the more you know about what is happening, the easier it will be for you to make risk mitigation, to follow risk mitigation procedures, or to make decisions at an earlier stage. In order to achieve this, you need to have a clear common operational picture. So we are putting together technologies, and we're going to utilize technologies, we'll explain how, that are going to give us a clear common operating picture between the various partners of the project, so that the final product, it is going to provide a good understanding of what is happening at the time in the theater of operation. And finally, after we have achieved all this, to provide optimal management of operations at any scaling and complexity of disasters. In layman's terms, we look forward to creating technologies, we look forward to utilizing technologies, to integrating old and new technologies in order to provide to the decision maker, whoever may it be, the ability to make decisions, informed decisions, risk-informed decisions at an optimal time, so that there is optimal coverage for the first responder. How does it work? The figure on the right, I think to technical people, it is going to give like a good understanding, but let me just try to give you an overview. First of all, we're going to capitalize on the existing, the newly developed 5G next generation telecommunication capabilities. So we're going to use the new telecommunication environment in order to have faster communications, in order to have faster decisions, in order to have faster exchange. And we look forward to creating also where are we going to transmit information from? Actually, we're going to transmit information from the actual theater of operation. What is the best possible way to provide this information? Actually, via having a new generation wearable chest band of clothing, so smart clothing for the first responder. And we're actually at the moment developing new sensors, new health sensors, so that we know what is happening in the body of, with the body of the first responder. and we can provide him or her with the necessary information to protect themselves. With environmental sensors, because don't forget, it is not only what is happening in us, but what is happening in us, in our body, mostly relates to what is happening outside our body, the environment. And of course, to provide, let's say, an emergency button, emergency activated sensors that will provide feedback in case of a fatal accident or injury, so that we know how to go about this. And this is actually now in development. I would like to spend 30 seconds here or a minute just to say that despite the fact that this project started in the midst of the global pandemic, we have managed to find ways, innovative ways, unfortunately, to communicate, integrate, and develop the various parts of technologies that are foreseen in this project. I'm not going to go into a further explanation of the system architecture because I'm not a systems engineer or a computer scientist. I think it will make a lot of sense. I'm a chemical engineer, so I can tell you what is happening after, how we're going to use this, and I'm going to concentrate on that. But my colleagues at the consortium will be very happy to provide any possible explanation. So there is a technical part, but how do we implement this? We implement this in two ways. The first one is training. I will talk about this, and then later on I'm going to talk about the pilot studies. Training with the original proposal included training as a very important element. We thought that because of the global pandemic, training has to be a tool that we're going to engage end users. So what are we going to do? We have tried to use training as an important tool, as I said, in order to engage end users. The first training took place online in Valencia, in Spain, back in December 2020. Thankfully, we had the window of opportunity in early September 2021, and we managed to have the second training live. There is going to be a small video later on. If we have time, we're going to see that. The second training that took part in Limassol in Cyprus, organized by the team here in Cyprus, and we trained firefighters, first responders live in a hybrid format and online as well. And 2 weeks ago, or a week ago, actually, not even 2 weeks ago, a week ago, we had the third training, which took part in Greece, in Athens, in a Galleo city, where, as you understand, every time the technologies and the tools are more and more developed, and we give them a better understanding of that. There are pictures of the second training that I just spoke about that a few minutes ago. And a second important tool for us is that of pilot studies. Technologies are developed. We have pre-pilot already opportunities. We have done 2 pre-pilot opportunities, and we have tested technologies. But as you can understand, in a real operational environment, we need to create not large-scale exercises, but let's say small-scale exercises with the participation of actual first responders. The first one concentrates on a fire scenario. It is going to take place in autumn 2022, so in a few months from now in Cyprus. The second one deals with an earthquake, and it is going to happen it's going to take part in Greece, in Athens, again in autumn, in late autumn 2022. And then as the project will be drawing to an end in the beginning of spring of 2023, we're going to go to Spain for the final large-scale pilot study. Just a few details if anyone is interested about the first one. It is going to take place, as I said, in Limassol. It concentrates mostly on fire, and the main focus is on enhanced situational awareness. The second one will take place in Athens, and it deals mostly with an earthquake scenario. We're going to implement 5G technologies there. So there is a focus on the geophysical part. And finally, we're going to go to Valencia, where we're going to include a robust global scenario where all the technologies are going to be tested there. We had challenges during the beginning of the project, mainly related to COVID. We had some limitations because of COVID again, due to COVID for the delivery of training programs. And we managed to overcome this. We, I think, had, well, I don't want to judge I think, like the reviewers should be judging that. So far, things have been going smoothly. We look forward to collaborating with external actors from the project, and this is an effort that we're putting in together now. Very thankful to all the colleagues. We have large industries, first responders, SMEs, research institutes and universities. Let me see if my video is going to work. If it works, yes, and it seems to work, then we're going to have a very quick 2-minute presentation of what took place in Limassol very recently. I don't know if you can hear the music, but it is very lively. Doesn't matter. It was a very sunny day. Very soon, like my words are gonna finish, so you're gonna see practice, so there is no need for actual sound. You can understand how important it is when it comes to training first responders in new technologies, because we have to realize that the scientific community usually is going very actively in trying to provide new technologies. The reality, though, is that we have to find the pace, and we have to find the space and the time in order to collaborate with our first responders, because it doesn't necessarily mean that they are always ready to integrate and understand the technologies and what is actually needed in order to achieve all that. Without further ado, I would like to thank you very much for providing us the space and the time to be here with you today. And as I said before, we look forward to expanding our collaborations. Japan is a very important partner for Europe and the European Union when it comes to technologies. Unfortunately, Japan is also very prone to natural catastrophes. So we have challenges, especially this part of the world here, that we have earthquakes, we have fires and all that, a common picture with what is happening in Japan. And we look forward to engaging even further. Thank you very much.
Hello, I am Rosette Maréchal from CS Group, and I am coordinator of the Intrepid project. I'm here to present you the Intrepid project in the scope of the Faster EU Japan Symposium. First, let's focus on the Intrepid concept. The context of the project is the observation that first responders face many threats and challenges in the earliest phases of a natural or man-made disaster. That is, first responders have to understand the terrain, to understand what happened, to enter the zone safely and to reach the right places, to localize and identify threats, but also victims, and to decide with very little information. Indeed, information is at the core of the whole process. It's scarce, it's unconfirmed, it's difficult to obtain, but it is crucial to decide on the right course of action and to save lives. The Intrepid concept is indeed based on the Prometheus movie by Ridley Scott, in which a team explore caves with drones and with this information generate a holographic view of the site and localize such threats. So we aim to be this kind of platform. The idea is to use the emerging technologies to improve the speed and safety of complex disaster site exploration, to improve the awareness of the environment, and to interpret all the collected data to support decision making in an intelligent way. So Intrepid focus on the earliest phase of a disaster in complex environment and most above everything, buildings and buildings incidents. The objective of the Intrepid project is threefold. First, to assist exploration by using cybernetic assistance to collaborate to scout and assess disaster zones. Second, understanding by using extended reality and artificial intelligence technologies to provide clear situational awareness. And then deciding by using intelligence amplification technologies to provide guidance, alerts, and decision support to first responders. The operational use is at the center of the platform definition. The platform is easy to deploy, it's scalable, it's secured, and its aim is to enhance the speed, range, and safety of disaster area exploration. A few data about Intrepid. We started in October 2020. The project lasts 36 months or 3 years. And the consortium consists in 17 partners from 9 countries. We have 7 technological partners, most SME and research institutes and universities. We have 3 support partners to address ethics and legal support, communication dissemination, and crisis management expertise. And then we have 7 end users from 5 countries, and all our 7 users represent LEA, firefighters, medical emergency services, and search and rescue organizations. This allows the project to have a very wide approach to the disaster management. Here you can see the whole Intrepid consortium. So now let's focus on the architecture and the technologies involved for first responders. Intrepid is built from the ground to the command center. It is an all-inclusive platform, an autonomous platform that not only takes into account ground aspects by providing cyber and physical agents such as drones or robots to assist first responders on the ground. It provides a tactical communication system to enable all the agents to communicate among them. It provides front ends to enable, again, all agents to have a view adapted to their need. And at the core of the Intrepid platform, it consists of several modules that provide information, very basic information such as positioning, for instance, up to the high-level information such as smart navigation, intelligence amplification, or doctrine modeling. All the information translated through a Kafka message broker to enable all modules to be independent and to collaborate together. First, let's focus on the ground modules, that is the UAV and UGV, the drones and the robots. First, the drones, smart unmanned aerial vehicles. It's a twofold module based on first an indoor drone model for exploring cluttered and confined areas, and then an outdoor drone for quick mapping of very large zones. Their main functionalities is to provide autonomous positioning and navigation in order to avoid first responder having to pilot the drones step by step. All these drones have autonomous navigation and positioning capabilities that enable them to navigate complex buildings. Other drones have plug-and-play sensors for thorough exploration and hazard detection, that is not only cameras, but also LiDARs and chemical sensors. And finally, other drones enable collaborative works, not only between drones, that is swarm mode, but also between drones and robots we will see afterwards. Their role is to enable autonomous, quick, and complete exploration of the disaster area, indoor and outdoor, visible and invisible, by providing a thorough 360-degree hazard detection and situational assessment. Not only physical 3D mapping, but also including, for instance, chemical information or CNRB information. Then the second aspect of the ground agents are the ground vehicles, the robots. In the case of Intrepid, it's a wheeled and legged robot with an articulated arm. Its main functionalities is to have a high capacity for obstacle trespassing, to be able to manipulate environments thanks to its articulated arm, to have autonomous navigation also, just like drones, and to carry cameras and LiDAR sensor for 3D mapping. Its role is to be able to circulate autonomously in complex and cluttered buildings, which include manipulating elevators, stairs, drones, which enable it to explore and to act on its environment. It can interact with this environment by operating switches, by picking up objects or placing objects in the scene. And finally, it provides support to drones by transporting them or to enable them to charge their own battery. Now, beyond the agent, another module is to enable real-time 3D positioning of all the agents, which involves not only UAV, UGV, but also first responders. It's called the real-time positioning module, and it's a flexible and multi-level positioning system for both indoor and outdoor positioning of agent. By multi-level, it means a multi-level accuracy from base to medium to advanced, according to the needs and the requirements of each agent. For instance, in this schema, you can see that advanced RTPM is placed on the UGV, and base and medium positioning system have been placed on first responders, for instance, with show-mounted device. The other main functionality of the real-time positioning module is to enable a seamless indoor and outdoor positioning, even in low visibility, by combining different algorithms and positioning systems such as IMU, GPS, SLAM, etc. Its role is to provide adequate positioning of each agent on the ground, regardless of the context of pre-existing infrastructure, by using all the algorithms and all the positioning techniques that are possible right now. And you can see here on the last picture a representation of the positioning device within a small robots that can navigate throughout the building, the demonstration building. So once we have the agent of the ground correctly positioned, able to collect data, all this data and all this position information is brought together through the situational awareness modules. The first situational awareness module is the environment mapping module. It's a real-time 3D model construction with automatic presentation with an initial BIM model. Its main functionalities is to provide BIM modeling from drawing, blueprints, so this is in advance, but then also while in operation from 3D data and photos. It provides also alignment of data acquired in operation with the initial BIM model built from drawing, blueprints, or pre-existing 3D data. It provides also Also in operation, it provides occupancy grids and change detection during operation to support navigation and path planning in real time. Its role is to update and enhance the 3D representation of the disaster area during the operation to match the ground reality, because the 3D model that is available before the disaster may not be the reality of the building or the structure right now. And this update enables a safe navigation and path planning of all agents in operation. The second situational awareness module is the object detection modules. It detects and notifies objects of interest from data flow provided by agent. Its main functionalities is, of course, object detection from RGBD and thermal images acquired, for instance, by UAV or UGV. You can see here example of person detection from thermal images and for RGBD images. But not only that, it also provides positioning and classification of detection by providing them a priority and a level of confidence to each detection. And finally, it's algorithms that are evaluative and trained on dataset, which means it improves as it goes. Its role is to exploit the UXV data flow to automatically enrich the situational awareness and to increase operation safety and efficiency by detecting obstacles, hazards, victims, etc. All this information, be it positioning, data flow itself, or process information through situational awareness modules, are presented in the Intrepid fronthend. Intrepid fronthend are threefold. First, the desktop fronthend, which I will not present today because it will be a bit too long, an air fronthend, and a mobile station fronthend. So first, the mobile system fronthend, it's on-the-go mobile station with scope and operation management capabilities. Its main functionalities is first to present adapted situation awareness for first responder in operation. The adapted aspect is dealt with co-creation session, which we will discuss later, in order to really design the interface adequate for first responder needs. It also includes mission and incident management capabilities that be able to acknowledge missions, to inform of the end of a mission, and to inform of incidents and take pictures, for instance. And finally, it enables push-to-talk and screenless communication with all the other agents of the platform. Its role is to provide first responder with tailored and adapted situational information, but also to enable multi-channel communication capabilities with a single interface. And by multi-channel, we mean incident management, push-to-talk, voice communication, data communication, pictures, upload, etc., with a single interface, which consists in a smartphone with a dedicated Bluetooth button to avoid screen interaction. The second fronthend we will focus on is the augmented reality COP, which is a portable air-based visualization of beam-based combination operational picture. You can see here an artist's view of this, what is consistent. So you have the beam here, the beam model of the building, which we can manipulate and interact with gestures. Its main functionalities is to provide an immersive and interactive rendering of the situation. It's portable, it's HoloLens based, and it provides a real-time update of the agents and of events, positions, and status with dedicated visual metaphors. Its role is to provide command center of all types with an interactive and immediately understandable view of the situation for a quick and efficient situational awareness of all levels of the command centers. So we have seen a very operational modules from the ground to the positioning, then interpretation through situational awareness modules, and visualization to front ends. We will now focus on the most innovative and advanced module, intelligence amplification modules, which are the smart navigation modules and the twofold tools, doctrine modeling and intelligence amplification. The smart navigation modules is the path planning module. It's an intelligent path planning algorithm with real-time inclusion of hazards and obstacles. Its main functionalities is to take into account the beam model characteristics, that is, taking into account the notion of rooms, doors, windows, stairs, exits, etc. Then generate a graph-based path generation taking into account this structure. But then it weights each path and prioritizes them according to the distance and safety. And safety is provided by real-time taking into account of detections and incidents within the building. You can see an example of different steps and different paths that are possible from start to target. But some of them are deemed unsafe because, for instance, hazards of fires have been detected. So the path planning module will provide reliable guidance based on the real-time situation assessments of the building and of the graphs for increased efficiency and safety of first responders and UXV. Then the twofold doctrine modeling and intelligence amplification modules. So for the doctrine modeling, it's the modeling of decision-making processes and mission definition to support operation. It occurs before operation as a preparation work and platform enrichment, platform configuration, so to speak. Its main functionalities is to provide intuitive doctrine modeling interface by allowing users to design graph-like processes and graph-like protocols, and then to have interconnection with the rest of the platform for automatic update of doctrine library in a computer understandable way. Its role is to enable first responders to define and collect processes and mission in advance. And then while in operation, to alleviate common decision making during operation by having all this information, all this process, and all this protocol stored in a doctrine library. So they are stored, but they have to be used. And this is the work of intelligence amplification recommendation engine, which is based on predefined background knowledge, which is the doctrine model we talked just before, but also on current situational facts. Its main functionalities is first to enable the parallel use of doctrine models, that is protocols, missions, instructions, but also of situational information, that is current agent status, current agent position, current optimal path as computed by the path planning module. It allows a common enrichment of pre-existing models with learned premises while in operation in a new world symbolic integration. Its role is to support user decision by handling high complexity and data-rich situations, to extract processes, and to extract action recommendation. So you can see an example of a graph with a prerequisite set of missions that have been extracted for the doctrine model, and then a set of high-level mission. And the recommendation engine will decide from all this mission, depending on the current situation, what should be done first and by whom. Now we have discussed all these modules that are both on the ground and in the command center, but then all these modules have to communicate with each other. And this is the work of the Tactical Communication System, the TCS. In a disaster area, we cannot rely on a pre-existing network, which may or may not exist. So the Intrepid rely on the Tactical Network System, which is a dedicated, autonomous, and secured communication system completely dedicated to the Intrepid platform. Its main functionalities is a LTE 4G bubble-based design, which means each team can have its own tactical bubble thanks to a set of different devices from the most portable to the less portable. It's extendable thanks to extended devices, for instance, this range extender, which can be carried by first responders, but also by UGV. It's secured, it's high bandwidth, and easy to deploy in order to enable quick operation. Its role is to provide a quick and efficient network in operation in all situations, be it indoor, outdoor, with or without a pre-existing network. Now we have discussed all the technologies of Intrepid. Let's discuss the process, which is from the start a very user-centered process, from the requirement definition to the field validation to the pilots. The project development itself is based on 3 phases to ensure proper acknowledgement of user requirements and feedback. We have a 3-year project, and roughly 1 year is a phase We have the alpha phase, beta phase, and final phase. Each phase closes up with a pilot and corresponding requirement update. Throughout the project, co-creation sessions are organized and animated to enable first technologies introduction at the start of the project. What can technologies do? Then use case identification and refinement. What can technology be used for? And then interaction and interface definition and assessment. How can technology be used best? How can we help end user use technologies and understand technologies best? Regular pilots through the project and demonstration enable users and community to give feedback on usability and compliance of the module with the need of the first responders. So unlike classical layout, we don't have pilots at the end of the project, but really throughout the project. As mentioned, the consortium is accompanied by a whole community and mainly by two major bodies that are really crucial and involved in the project from day one. The first body is the External Advisory Board with a 10+ member body that provides advice and feedback on requirements for further user-centered design, and that also participates to pilots and demonstration. And then Security, Ethics and Legal Advisory Board, which is a 5-member body formed by independent SEL experts that ensures that all steps of the Intrepid projects fully comply with the most up-to-date regulation regarding security and ethics. The involvement of end users do not stop at requirement definition, but also it's included in the field validation methodology, which is an innovative field validation methodology that is carried through the project. It's a continuous process that starts with scenario design by defining parameters and micro scenario, to demonstration, data collection pre and current test, collecting data, and post-test data analysis. The backbone of this methodology is the use of the expected value information. This expected value information is user-centered and user-defined by identifying hotspot and operational issues. And then each module is assessed against these expected values beyond, I would say, theoretical KPIs. As mentioned before, pilots are organized throughout the project and not only at the end. The first pilot was set up after the first year of the project in November 2021. It was in Stockholm and it involved the assessment of the technical choice in a very controlled environment, that is a subway station that has been privatized for the project. Now we are currently preparing the second pilot, which will occur in October 2022. It will involve an industrial accident at the service site in Marseille, and all the modules will be brought together to assess a multiple risk situation with fire, smoke case, chemical risk, nuclear risk, and structural damages of the buildings. The third pilot, which takes place in May 2023 in Madrid, it will involve an explosion in an office building and will bring the platform step above by dealing with unidentified risks and to need the police and first responder cooperation with a potential malevolent actors. So now let's end with the current status of the project. So you can see here the 3 phases of the project. The first phase, the alpha phase, stopped in November 2021 with the first pilot and the associated update of the requirements. We are currently working on the beta phase, which will end up in October 2022 with a second pilot in Marseille. And finally, we will deal with the final phase, which will end up, well, maybe not in September 2022 because it will be the end of the project, but the final pilot is planned in May 2023. If you want to be informed of the further development of the project, you can see here how to contact us. So with the website, Twitter account, LinkedIn account, or Facebook account. Thank you so much of your attention and looking forward to discussing Intrepid with you.
Hello, my name is Konstantinos Konstantoudakis. I'm a researcher at CERT, and I will be presenting the Rescue project. So, first of all, the identity of the project. This is a project funded by the European Commission. It started on July 2021, so it's currently on month 9. It has an expected duration of 36 months, and it comprises of 20 partners from 9 European countries, including 7 research institutes or universities, 5 industrial or SME partners, and 8 disaster response organizations. A few words about the motivation of Rescuer. So there have been many rescue-related research projects that bring emerging and innovative technologies to first responders, including drones, robots, 5G communications or other high bandwidth communications, cloud computing, or satellite services. However, sometimes first responders need to operate in less than perfect conditions. Many or all of the above technologies may not be available all the time. This situation also tends to be the most dangerous both for first responders and for civilians caught up in a disaster scene. Hence, Rescuer aims to provide a set of technological tools for first responders for hostile and infrastructure-less environments. It views the first responder either as an individual unit or a part of a small team. It focuses on hostile environments like adverse weather, low light, or noise, and infrastructure-less environments. So environments without external devices like robots or drones, without communications or access to cloud resources, without satellite access. It aims to provide tools to be carried by individual first responders on their own person so that they are not dependent on any external communication or server or device, and also to provide communication and sharing among a small team of first responders, even though the normal communication channels might be unavailable. Now, I will present the technologies of Rescuer. They can be grouped into 5 different categories. The first category is augmented senses. So we have augmented vision, which focuses on vision in adverse conditions like rain or fog or smoke or darkness, and how to make artificial intelligent algorithms be able to work in these conditions and identify things important for the first responder. Augmented hearing, which aims to suppress noise and make sounds that are important for the first responders, like their teammates talking or a victim crying for help, or other important sounds easier to hear among the noise. Augmented olfaction, that is smell, which means the detection of dangerous gases. It's not really smell, but it is the detection of dangerous gases by some specialized sensors. A remote touch, which is radar sense, which aims to warn first responders of obstacles in smoke or darkness. And the detection of signs of life, to see if there are living people on the far side of a wall. Even though you cannot see it, you can detect them through the wall. The second group of technologies are localization technologies. These focus mostly on self-localization so that individual first responders can understand where they are at any given time. We have 3 different technologies to aid localization. Vision-based, which means that much as a person looks around and understands where they are, if they have seen that place before. IMU-based localization, of course, and satellite-based localization in case a satellite connection is available. This will be considered both individually and in fusion so that we can have more robust and better understanding of each first responder's location. The other part of this group is victim localization. Sometimes victims can be buried under rubble, lost in smoke or darkness, or maybe even under snow. However, most people will carry wireless devices like a smartphone with them, and these can be detected using GSM, Wi-Fi, or Bluetooth. So this can lead to the first responder locating a victim more easily. The next group of technologies are communications. Internal communication is about collecting all the output from all the other tools so that they can be used in some way. Communications with the other members of the team, even though the normal communication channels like mobile communications are unavailable, will be taken care of in an ad hoc way. So we will use Bluetooth or Wi-Fi to build ad hoc communication networks so that the team can communicate with each other. Communication to the command center in case such a connection is available. Communication with buildings. We will equip some buildings with what we call a building black box. This is analogous to the well-known aircraft black boxes, of course. So the building black box will store information from building sensors, like how many people are in the room, if there was a smoke alarm in one room, if there was a fire alarm, if there is a door open. And the first responder team entering the building will automatically access this information and so know some things about the building they're about to operate in. Finally, of course, we have the orchestration and sharing of all of this information, which is collected, so that it can be shared to other first responders or visualized or processed in some way. The fourth group of technologies is about mental health. Of course, we know first responders operate in stressful environments. All of the other tools will generate a lot of information, but too much information can be confusing or distracting to a first responder, and this can be a very dangerous thing to happen during an operation. So this will focus on prioritizing information and tracking the cognitive load of each first responder using their biosignals, like breathing rate, heart rate, temperature, etc., so that we can balance this cognitive load and present to them the amount of information and the way of displaying this information that is helpful and not distracting. At the same time, we will monitor the long-term mental health of first responders, tracking which kind of conditions make them more stressed and what is the long-term impact of that. Finally, everything comes together in the visualization so that all of the information that is collected and generated by all tools will be visualized in augmented reality in two different devices. One device is, of course, the Microsoft HoloLens 2, which is the state of the art in augmented reality at the moment, being able to project three-dimensional holograms. However, the HoloLens 2 is not ready for operational use. So for this reason, Rescuer is also developing the Rescuer Situational Awareness Helmet, which is a normal first responder helmet. So it provides all the protection that a first responder would need on their head. And it integrates an augmented reality screen, a smart battery pack, and the processing unit, so that the information can be displayed in a two-dimensional augmented reality way, while also providing the first responder with protection. Now here we have an overview of the Rescuer system. The left hand of the circle is the core of the Rescuer technologies, and all of these are devices and tools that will be placed on the first responder themselves and not be dependent on any outside source. This includes sensors like cameras, microphones, inertial sensors, biometric sensors, radars, gas sensors, and everything that is needed to sense everything. And also, of course, the visualization devices, which is either the HoloLens or the smart helmet. On the right hand of the circle, we have the external connections. These are not the core connections of Rescuer, since Rescuer considers the possibility that no connection is available, but we still plan to support this. So we have the connection to the command and control center, the connection to other team members through the ad hoc communication network, and the connection to building by the building black box. Everything is coming together in a gateway device, which need not necessarily be a phone, but it will be a small portable device which will collect everything from all sources and orchestrate and prioritize and share appropriate information to where it needs to go to be most effective. Rescuer has planned for 3 different use cases, where each use case will be focusing on a different set of adverse conditions or lack of infrastructure. So we have the earthquake use case, which will be held in an urban setting in Germany. This will involve, among other things, collapsed walls, victims that may be trapped under rubble or inside rooms, a lot of noise, and of course, black boxes, which will be able to track what's happening inside the buildings. The second use case is a hazmat incident in a tunnel in France. So we're in a tunnel, so we have, of course, no GPS, there may be darkness or smoke, and there will be dangerous gases since this is a hazmat incident. The final use case is a hiking rescue scenario, which will be held on a mountain in Spain. We plan to include adverse weather conditions, such as rain or snow, as the case might be. We may have victims buried under snow, and of course, since this is a mountain, we will have large distances to cover. Each use case will hold 2 pilots, one near the middle of the project timeline and one near the end, where the technologies will be more mature and more integrated. So we will have a total of 6 pilots. This is more or less Rescuer in a nutshell. And before I end this presentation, I would like to also share with you a very nice promotional video that was created by our communications team. Thank you for bearing with me. Goodbye. That was it.